Yeah, good morning everyone. So today we are discussing about the basics of digital electronics. So this is the important topic of the digital electronics total subject. So here what is meant by the digital electronics? So when you see the digital electronics is the foundation of modern computers and digital communications. So in today's digital era, we are using the different types of the communication devices and the electronic devices, so which are made of with logic circuits. So logic circuits means which are having a millions of gates that can be what is that can be constructed by using different types of the transistors. After that, integrated circuits like microprocessors and different types of circuits we are using. Those circuits can perform a millions of operations in a second. So digital techniques are used here for easier of operation to an electronic device to switch from one state of circuit to another states. So continuously taking some range of values here. So many advantages are present by using the digital circuits when compared to the analog circuits, because the analog circuits are having taking very much of what is it time, and also so much of noise will get when we are operating that circuits. So whereas in the case of the digital circuits, it can be transformed to the larger distances and faster responding time, and very much less time it takes, and also very much less noise prone devices that is present when we are using the digital circuits. So here in this, the first topic we are having, that is called as number systems. So it is a most important topic. It is a fundamental topic for all the digital electronics, all the different units and the microprocessors also. So basically, what is meant by a number? A number is a representation of a quantity. So here, how we are indicating the quantity? A quantity is can be represented by using a number here. So by using certain symbols, a quantity of things can be expressed. So here we are using some of the digits like values. Instead of writing in words, a value can be used to write in a symbol form. So this symbolic representation is must to perform various mathematical operations like addition, subtraction, multiplication and division. So basically we are using two types of the number systems. One is called as non-positional number system, and second one is the positional number system. So what is meant by non-positional number system? So it is the what is a non-position. The name itself we are having it. What is that? In this number system, for each number there is no positional weight is present here. For example, when we take that Roman number systems like 1, 5, 10, so we are indicating with some of the what is that symbols, some of the what is that quantity numbers we are using. So these digits are having no positional weights. There is no weight that can be contained for this what is that Arabic Roman numbers. So that's why it is called as non-positional number system. Next, second number system we are having, that is called as positional number system. So it is most widely used number system. So in this system, the position of a digit indicates the significance to be attached to that device. Okay, for each number we are writing in this number system, for each digit, what is that? A position is mentioned, specified here. So there are many positional number systems are present. So in that we are using the four basic positional number systems. They are called as, first one is the decimal number system, second one is binary number system, third one is octal number system, and fourth one is the hexadecimal number system. So in all these number systems we are using one term that is called as base or radix. So what is meant by base or radix? The number of symbols that can be used in a number system, that is represented by using one term that is called as base or radix. So it is always one more than the highest digit of the system. So when we see the different types of the number systems, so the first one is the binary number system. The number system with base 2. Okay, that means the two number of digits are present, two number of symbols are present in this number system. The type of number system is called as binary number system. Okay, already we know that binary means 2. So the binary number system having two symbols, they are called as 0 and 1. The symbol 0 or 1, it is called a bit instead of calling a binary digit. Okay, so the example we are having that 1011, 1010, 1000, like this. These are the examples of the binary numbers. So the binary number system is also a positional number system where in each binary digit has its own value or weight expressed as a power of 2. We are representing each digit positional number. So we are writing that binary number, that is a power of 2 here. Next, octal number system. The number system with base 8 is known as octal number system. So already we know that, okay, base represents the number of symbols here. So in this system we are having the 8 symbols are present, 0, 1, 2, 3, 4, 5, 6, 7. So these are used to represent the numbers. Okay, for example, when we take the numbers 13, 143, 2, 3, 4, 7, okay, all these are the examples of the octal number system. So the next one we are, what is that we are having? So we are representing that octal number system in the power of 2 power of 3. That means every 3-bit group of binary that can be represented by an octal digit here. So similar to the decimal and binary number system, we are also having a positional number system. And in this also, what is that? One more thing, that is octal number system. After that, we are having the decimal number system. So that is a decimal number system has a base of 10. That means 10 different symbols are present in that number system, and that is our 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, up to 9 are the decimal number system. Next one, hexadecimal number system. When we take the hexadecimal number system, it has 16. The base or radix value for the hexadecimal number system is 16. So that means 16 different symbols are present in this hexadecimal number system. So here it is a combination of alphabets and numerical numbers. So 0 to 9 are the numbers it is present, and A to F are the alphabets that is used in this number system. So example 2009, 924, A23. Okay, so different types of the combination of alphabets and numerical numbers are present in the hexadecimal number system. So here, next, when we compare the above number system with other number systems like decimal number system, okay, so decimal means 10 here. We are having the values of 0 to 9 are present, and so these are the important tabular column that is given here, representing that binary, octal, decimal, hexadecimal, with binary base 2, octal base 8, decimal base 10, and hexadecimal base 16. It is a combination of alphabets and numerical numbers also. So different digits what are used, we are using different number systems, and what are the basis of the number systems that is given. So next, when we see that how to convert one number system into the another number system. For example, when we have to convert the decimal number system into binary system, so in this case, first, what is that? The given binary decimal consists of the both integer part and fraction parts. There are two cases are present here when the decimal number is given. So in that case, integer part is present and fractional part is present. So how to convert this integer and fractional part into equivalent binary integer part and fractional part that is given here. So when we see the case 1, decimal integer part, so to convert a decimal integer part to binary number, the decimal number is successfully divided by 2, and the remainders are recorded after each division until the quotient is 0 here. Okay, so when we divide a decimal number 13 by this, what is that? So dividing that given number by 13, we get the quotient of 6, and the remainder is 1. The 6 is then again divided by 2, giving a quotient of 3, and the remainder is 0. So this process is carried out until the quotient becomes 0 here. Okay, note that the first remainder is the LSB and the last remainder is the MSB. So we are writing that the numbers from top to downwards to the upwards here. So you have to remember that when we are dividing that decimal integer part, so here we have to write that result from downwards to the upwards. This is the important point in this case. So when we completed this division, we can write that the binary equivalent of the decimal number 13 is 1101 base 2. Okay, 13 base 10 means it is a decimal number. 1101 base 2 means it is a equivalent binary number. Next, how to convert a decimal fractional part into binary fractional part. So first we are considering a fractional part like 0.875. So here in the case of the integer part we were divided with 2, but here in the case of the fractional part we have to multiply with 2. So multiplying it by 2 will get the result of 1.750. So in this case we are taking that what is that the carry that is called as integer part reside, that is 1 point in the 1.75 we are taking that one integer part. So after that next fractional part that is multiplied with 2, that means 0.75 is multiplied with 2. In that case we will get 1.50. So when 1.50 integer part is 1 is there and fractional part is 0.50 is there. So after that next step, in the next step 0.50 is multiplied with 2, so we are getting 1.0. That means integer part is 1. So when we see that in the case of the integer part how you are written the numbers, the result that is written from downwards to topwards. But in the case of the fractional part we have to write it down that result from upwards to downwards by putting a what is it the decimal point here. So that means the equivalent binary equivalent for this given decimal number 0.875 base 10, that is 0.111 base 2. Okay, so here this is a conversion process for the decimal number, given decimal number in the case of the integer part and a fractional part into the equivalent binary integer part and also the fractional part. So the next one here it is given, one of the example is also given. So how to convert 0.95 decimal number into its equivalent binary number. So multiplying, we are multiplying that 0.95 with 2, then we are getting 1.9, that means integer part is 1. After that we are multiplying 0.9 with 2, then we are getting 1.8, taking the integer part 1. Next 0.8 is multiplied with 2, next we are getting 1.6, that means integer part is 1. Next 0.66 again multiplied with 2, we are getting 1.2 as the result. So in this case also integer part is 1. Next 0.2 is again multiplied with 2, we are getting 0.4. So in this case integer part is 0. Next 0.4 is again multiplied with 2, we are getting 0.8 with 0 integer part. So after that 0.8 is again multiplied with 2, then we are getting 1.6. So here when we have to multiply this one with again 0.6 means already in the third step. Okay, in the fourth step already we have multiplied that 0.6, that means it is again repeated. So when we get this repeated values like this, we have to stop this multiplication and we can write that result with by putting the decimal point here. So the binary equivalent for the decimal number 0.95 base 10, that is 0.11111411001 base 2. So here you have to remember one point here. In this case 0.8 is repeated, and if we multiply further we will get the repeated sequence here. So that's why we are stopping that the process for the repeated values here. Okay, so next how to convert the decimal number 37 into the binary equivalent. So here also we are dividing that number because it is an integer number, so we can divide that number into successful divisions with base 2 here. Okay, so we can divide that one, and at last we are writing that result from downwards to topwards, that is MSB first and LSB is the last because it is the integer part. So the binary equivalent of the decimal number 37, that is what is that, the result is 100101 base 2. So like this we can convert the decimal numbers, given decimal numbers in the form of the integer parts and also in the form of the fractional part. So here only you have to remember the remembering point here in these two cases are when we are what is that when we are converting that integer part, we have to divide with 2. When we are converting the fractional part, we have to multiply with 2. And when we are writing after conversion, to write that result in the case of the integer part, we have to start from down and go to upwards. And when we are writing the result of the fractional part, we have to move from top to downwards. So it is given 157, the result that is also given here. 125 integer part is, that is dividing, and 0.8125 it is the fractional part is given. So the result is 0.1101 by writing topwards to downwards. So some of the numbers also containing both integer part and fractional part, like 26.15 base 10. So it is having that integer part is 26 and fractional part is 0.15. So here 26 is divided with 2, like successful divisions are present, and after that writing that result from downwards to topwards. So that is 26 equal number is 11010 base 2. So whereas for the fractional part we are multiplying with 2, like 0.15 is multiplied with 2. So here we are getting up to 1.6, that is to up to getting for the repeated value we are multiplying it again and again. So at last what is the result? 0.15 equivalent binary number is 0.001001 base 2. So here integer part is separately we got it, and fractional part is separately we got it. So the given problem contains both the integer and fractional part, so we have to combine both the integer and the fractional part in the result also. So 26.15 the binary equivalent number is 11010.001001 base 2. So this is what how to convert the given decimal number into binary number which has both integer part and the fractional part. So the next example also given, that is 41.7. It also contains both integer part and fractional part. So integer part is successfully divided with 2. After that we are getting a result of 101001 base 2, and for fractional part we are having that result 0.7, that is 0.10116. By combining both 41.7 we are getting that result binary equivalent 101001.10110 base 2. Okay. So this is the conversion process for converting that given decimal number into a binary equivalent number. That means base 10, we are converting the number base 10 into base 2. So in the next hours we are discussing about the decimal number into capital number. Thank you.